Until now, we have talked about the complexity of executing a program once with one size of input. We have the big O, big theta, and big omega notations, but until now we have used them to express the complexity of one single run of a program. Consider this graph that denotes the complexity of an algorithm. For the most part, the execution time is constant, but there are some spikes here and there. The spikes seem to increase in size, but on the other hand, they also seem to occur more and more rarely. Amortized analysis deals with the complexity of performing the same operation multiple times for varying inputs. For example, inserting multiple elements in a data structure. As an example, consider an algorithm that has a worst-case complexity of big O of 1 for the majority of the input. That is, it only uses a constant amount of instructions to complete. However, every now and then, the algorithm needs to perform some housekeeping in order to be able to provide this good big O of 1 performance. And this housekeeping results in the algorithm to use big O of n instructions to complete, where n refers to call number n. Let's say that it is being called m times. What is the total complexity of these m calls? In the good case, with no housekeeping, we have a complexity of only big O of m. And in the worst case, it would have a complexity of big O of m times n. The interesting question to ask is whether this recurring housekeeping has any significant impact on the performance when the operation is called multiple times. That depends on two things: the frequency of which this housekeeping occurs and the complexity of the housekeeping. If things are designed sufficiently cleverly, the cost of the housekeeping will even out, so to speak, upon multiple calls. I'll end the description about amortized complexity for now, but we'll come back to it in the module about data structures.